Good morning, everybody. Bright and early here, last day of the show. Thank you for coming. I'd like to introduce myself. My name is David Donkin. I work for a company called UCC Environmental. This is a privately held corporation that's been in existence for 104 years. Most of our existence, we served the coal-fired power industry in the business of moving material, specifically fly ash and bottom ash, and building systems that get that material out of the powerhouse in a convenient and efficient manner. In the course of time, about 2008, we expanded our offering to include air emissions control products, which we also promoted throughout the coal-fired power fleet in the United States. And then about 5 years ago, made the decision to further expand our offering into wastewater treatment, principally for this market as well. And that was when I joined the company. I was the first outside hire subject matter expert that came on board to help build out this wastewater treatment team. And we now have a number of technologists and folks that help us promote all sorts of solutions, not just the topic today, but for FGD scrubber wastewater, pond closure wastewater, things of that nature. We spend a good deal of time promoting those technologies as well. I came to the company after about 25 years in industrial wastewater treatment, doing equipment design, sales, chemical treatment programs, sales and service. And I've been very fortunate. I've gotten to work in just about every industry out there. So I was real happy to join this team and help build out this offering. So with that, we will move on. Okay, great. I do have a brief safety moment. It's our practice in the power industry to start every meeting with a safety moment, and the topic today is carbon monoxide poisoning. You may or may not be aware that carbon monoxide is an odorless, invisible gas that evolves from inefficient combustion, typically from furnaces, generators, heaters, things of that nature. It's extremely poisonous. It can kill you in a matter of hours, sometimes minutes. And sometimes it can occur with very few symptoms that come on to warn you. The symptoms include nausea, confusion, vomiting, headaches, things of that nature. The reason I bring this up is there are carbon monoxide detectors now that work just like smoke alarms, and they're quite good at protecting people, but you may or may not be aware they have an expiration. And without going into all the statistics about how many people die from carbon monoxide poisoning, I just want to be transparent about my experience hearing the safety moment at a different meeting. I paid attention. I said, oh yeah, okay, that's a good point. And I have carbon monoxide detectors in my home. But the comment came up, you have to replace them every 7 years. The actual unit, not just the batteries. Because after 7 years, they're really not very efficient. And I thought, okay, well, I'm sure mine, I remember doing that a year ago. And kind of forgot about it till I got home. And then said, you know what, I want to see when I put that one in. And it turned out my unit was 11 years old. So it's easy to forget with these kind of devices how old they are. And it's easy to think that they're newer than they actually are. They may not even be working correctly. So that's my safety moment concerning carbon monoxide for today. So the topic at hand is concerns a process that goes on in coal-fired power utilities whereby the power utility uses sluice water to move bottom ash out of the bottom of the boiler. And if you're not familiar with these systems, I'm going to walk you through what they look like real quick and get you up to date on what the EPA has been doing with the steam electric power generating effluent guidelines, or the ELGs we call them in the business. This is a rule that was promulgated going back to 2012, I think, and there were lawsuits, and then it was rewritten, and then the goalposts moved again with respect to discharge limits, and then it was expanded, and it's an ever-evolving rule where we find ourselves today in the situation that the EPA is addressing the treatment, management, and discharge of what we call bottom ash transport water. So these systems pertain to what we call remote drag chain systems or submerged flight conveyors, and they refer to traditional dewatering bins with surge and settling tanks. These are devices that use hydraulic power or hydraulics to move ash out of the powerhouse, and then they go into these systems where the water is separated from the ash. This rule, by the way, does not pertain to what we call underboiler drag chains, because that water is classified as quench water, not transport water. So there are no discharge regulations right now for that water. So this is what a traditional dewatering bin setup with surge and settling tanks looks like. You've got your powerhouse back here, and the bottom ash drops into what we call bottom ash hoppers. And from here, the ash is sluiced out with we call them jet propulsion pumps. It's basically an ejector pump. It uses vast volumes of water to move the ash out of the powerhouse efficiently out to this system, which typically resides outside of the powerhouse proper. The water and ash goes into these dewatering bins where the ash is able to rest and settle, and from here the ash can be emptied into trucks that can drive underneath and taken either to landfill or to beneficiation reuse. The water overflows the dewatering bins into a settling tank, and the settling tanks function if there's any fine solids that remain from the ash. This is a place where those solids can be separated from the water. And then finally we have a surge tank, which is really there for water balance needs. Depending on how the units operate, these jet pumps will be turned on and off for what we call sluicing events. And they may run for an hour at a time, moving sometimes 5 to 10 tons worth of ash out of the powerhouse. So all the water associated with this in these configurations is typically recirculated. And again, this water is referred to as bottom ash transport water and does come under the new proposed regulations in terms of it, if any of it's discharged, what it has to be treated to, or even if it's allowed to be discharged. There's another configuration that is relevant to the rule, and that is what we call a remote submerged flight conveyor or a remote drag chain. Once again, here's your powerhouse, bottom ash hoppers, sluicing line with water and ash comes out to this unit. Water and ash goes into the center well here. The ash settles to the bottom of the unit and is conveyed out by a drag chain with a chain of flight system, and the ash is deposited into this bunker for dewatering. The water flows in this direction, and most systems today have been, we've made some advances in this technology. We use lamella plates to help facilitate settling of fine solids, and then that water can overflow to a surge tank or a clarifier and then be recirculated. And in the old world it could be discharged, but this is going away again under the rule. So I'm not going to read all this, but I cite it for anybody who wants to look it up. This is from the 2023 proposed rule release, by which 4 different options were discussed for bottom ash transport water discharges. And the essence of all of this is that the EPA is leaning very strongly toward option 3, which essentially provides provisions for treatment of overflow or slipstream treatment so that full 100% recycling of this water can be achieved. And the rule talks about some of the technologies that are available to accomplish that, including chemical addition, side stream treatment with filters and RO systems, and all sorts of other technologies are mentioned. And yes, here it goes through again more on the different options that may exist. So what are the implications? If we have to close these loops completely, and I should mention, in previous versions of the rule, there was discussion of what they called a purge provision. So if your sluicing water was getting more and more contaminated, building up minerals, maybe the pH was getting out of whack, there was a provision to release some of it out of the loop and then refresh it with fresh water to recreate a water balance or a chemistry balance. In the latest version of the rule, that purge has not really been discussed, and it may be eliminated entirely. The industry is pushing back on that, but there are conversations going on where these loops may be 100% recycled by the time the rule's finalized. So what are the implications for that? Well, if you know anything about water chemistry, when you have a closed loop water system and you have contaminants coming in, then you have the opportunity for minerals to cycle up. So the water gets saltier and saltier. The pH can start to swing in one direction or another. And naturally, with these two issues, you create either a scaling potential or a corrosion potential, or both. And with those come growing risks of operational problems, unplanned maintenance, and unplanned outages, all of which are things to be avoided in a power plant. So it turns out throughout the industry, certain utilities are very well aware of this problem. Other ones are becoming aware of it as they understand the rule. And UCC, we've spent an awful lot of time in the last 5 years studying these loops and trying to understand, all right, how does the water actually start to behave as it cycles up when we don't have purges? So like I said, we've studied a lot of different sites, looking at trends in water contamination changes and potential scaling problems. And for the purposes of this talk, I had 2 case studies that I wanted to discuss. And the first one is at a utility that has a traditional dewatering bin with surge and settling tanks. So as they've had their loop closed for some time, they began experiencing significant issues with suspended solids control. They also had trouble with scaling. We determined their Langolier saturation indices, which are a calculation we can do to see whether the water has a scaling tendency or a corrosive tendency. Numbers like this indicate a potential for scaling tendency. They're too high. I can just leave it at that for now. And their pH was significantly alkaline, which again contributes to a scaling phenomenon. Pictures are worth 1,000 words, and you can see right here this flange with a pipe has a very significant amount of scale inside. So naturally, this is going to impede performance of the sluicing system. And to bullet number 1, the suspended solids were completely out of control. This is the settling tank. This is designed really to do polishing on suspended solids removal. It's not supposed to look like this, which to me it looks like a sludge thickener at this point. So we undertook an investigation to figure out why this is happening and what we could do to help. And the first issue we wanted to address was the suspended solids. So after studying the plant for quite some time, they had worked with another vendor to try to solve this problem, and we've noticed that unfortunately they had made a number of errors. Perhaps they're not familiar with these systems enough to do this sort of study, but we were able to determine that first of all they had the wrong type of flocculant that they were using. So we did jar testing and screened a whole bunch of different products, and we're able to come up with one that would perform a whole lot better with respect to settling. The other error that they had made is they were injecting the flocculant in the wrong location. If you're at all familiar with flocculants, these are organic molecules that are very long chain carbons basically, and they have charge sites on them. The way they work in the water, they float around and grab onto any tiny particles and begin to flocculate them and get them all to gather together. So tiny little particles become bigger and bigger, and then they get fat and dense and heavy, and then they want to sink. So those tiny particles won't sink, but when you introduce a flocculant, you get those tiny particles to turn into big particles, and then they'll sink for you so you can clarify them out of the water. Well, these folks had injected this product, the wrong product, in the wrong location. They were injecting it on the suction side of a centrifugal pump. And what happens when you do that, the turbulence in a centrifugal pump will just shear that flocculant into smithereens, and it doesn't do its job because it's no longer a nice long molecule. It's been all chopped up into small molecules. We refer to that as shear. So we relocated the injection point, which helped an awful lot. And then finally we synced the dosing rate with the bottom ash transfer sequences, because this is a site where they would turn it on and off. And before, the flocculant dose was just on. So naturally that created a lot of issues. They were significantly overdosing the product. So this is the after picture. Again, we can go back to before. And that was the mess they had on their hands. And then after we straightened out the flocculant dosage, we have a nice swimming pool, which we like that a lot better. So once the suspended solids were resolved, then we could attack the dissolved solids chemistry challenges. And we had a couple of thoughts on that, but the first and simplest step and the most least expensive step was to simply use sulfuric acid to adjust pH down in the neutral range. And with that LSI calculation, you get your pH closer to neutral, you get into a range that you're no longer in a scaling environment. So we were able to hit these targets readily with just a simple, very small chemical injection skid. Dosing rate was slaved to a pH probe, and we managed to get the LSI much more under control. We also had the option to add scale inhibiting chemistry, but the client said, let's just wait on that. We'll see if we need it. I would argue it would be nice to have just as a belts and suspenders type solution, but scale inhibiting chemistries are very expensive, and these are large volumes. So, at $4 or $5 a pound, they've decided to wait on the scale inhibiting chemistry. So the conclusions on case 1, we have no apparent scaling once we've made these changes. We've resolved the solids plugging issues. The chemical dosing has met the expectations that we forecasted. We're holding off on scale inhibition, and we're just going to continue to study this site with regular visits and regular analyses and see whether we have solved the problem or not. So case 2 is with a different type of equipment scenario. This is the submerged flight conveyor that I referred to earlier. Once again, here's the powerhouse, bottom ash hoppers. Water and ash come out to this unit. They're introduced to the center well. Ash goes up the ramp and dewaters. Water goes in this direction to the next surge tank and so forth. So this was a site that we commissioned only a few years ago. It was a brand new installation. And right off the bat, we commissioned it with chemical injection because we had learned a few things. And we wanted them to have a nice clean system that would function well from day one. One of the distinctions between this type of ash dewatering system and the dewatering bins is the contact time between the water and the ash. The contact time with this type of system is only a matter of hours, where with the dewatering bins, it can be days. And the reason that's important, the longer the contact time with the ash, the more contaminants will transfer from the ash to the water. So we do have some advantages with this approach. Do we need to take cover? So probably should move a little faster. So in this case, we used flocculant addition, and we were able to maintain TSS on the overflow less than 100 ppm. We don't have a clarifier on this site, so the settling has to occur in the body of the SFC. The SFC has lamellas to assist with the settling, and the solids, as they accumulate, the fine solids, they accumulate kind of as a sludge, exit the system quite readily with the ash, and you can see a good depiction of that here. We've got a bunch of flocculated fines going up the ramp along with the bottom ash. With those fines removal, because again we're in a recirculation mode, we can reduce pump wear, we improve water treatability, and we get the suspended solids to go where they're supposed to go. They're not coming out in the wrong location. Here's a before and after of the surge tank just downstream of the SFC. This is without flocculant addition, and this is with flocculant addition. This has like a sun barrier, so it looks a little funny. This is a floating mat, so it doesn't look like a regular tank would look. You'd expect without that, so that might be a little confusing to see. But if you focus your eyes here and here, you can see the difference. Once again, we used sulfuric acid for pH control, and from day one we've maintained an LSI in a very acceptable range, not too corrosive, not too scaly. pH ranges between 6.14 to 7.84. And I always say so far, because you never know when something new is going to emerge, but so far we have no issues with scaling, no issues with solids plugging up any lines. Chemical use, once again, has met expectations. Client just like the first one, has opted to hold off on scale inhibitor chemistry, and they've asked us to continue to collect data and report on our findings. So this is where I get a little sarcastic, so I hope you'll bear with me, but I wanted to just comment about the proposed rule and how these terms have come up and my sort of objection as a technologist to some of the terminology. So they use the word closed loop. None of these systems are truly closed loop. You will have water that's still in the ash when it's disposed of. Now, it'll pass a paint filter test. There's no fluid running out of the ash, but there's still moisture in there. Same with any downstream clarifiers that are accumulating sludge. There's going to be an underflow. That underflow is going to have water in it. And there's going to be evaporation because ash is hot. So you do get a significant amount of evaporation in these loops. So you will have makeup water coming into these systems. And this is the thing I never put in print, but if you've been in any of these plants, some of them were built in the 50s, the 60s. You go into the basement of the powerhouse, and sometimes it's almost like a rainforest. There's leaks everywhere. They just leak. And, you know, it's not really nice to talk about, and it's not something anybody really wants to promote as, oh, look what how leaky our system is. It's just a reality in some of these facilities, and they do the best they can to capture this water, but they're not perfect. And then the rule talks about side stream filtration, and we're scratching our heads and wondering, all right, what's that going to look like? So here's what you have now. Here's what I just showed you. Bottom ash, SFC clarifier, water comes in this loop. To manage scaling, we add some chemistry. So what does the rule suggest? Well, they talk about filters and ROs. Okay, well, so does it look like this? We go from the clarifier, we take either part of the stream or the full stream. ROs require pre-treatment. If anyone's worked with a reverse osmosis, you know that. So you're going to have some filters. You might need a softener. I mean, I don't know. It depends on the water quality. But success or failure of an RO is going to depend on the pre-treatment. If you add scale control to that loop with chemistry, you know, maybe it looks more like this. Most of your flows go round and round, and we just take a tiny little side stream. That's a good solution because then all this expensive equipment gets a lot smaller. Maybe it's a little more palatable from a capital investment perspective. Where do the waste streams go? Well, you're going to have sludge off the clarifier, backwash from the filters. So we're going to need all this equipment too. You're going to need a thickener for the solids. You're going to need dewatering for the solids. Again, it's really not closed loop. These materials are going to leave this loop. Landfill, and then RO. ROs have reject. It's a significant volume compared to the input. What do we do with that? Well, if we're in a true ZLD, we're going to have to evaporate it. Well, then what's left? Solids with a little moisture in it. That's going to the landfill too. So there's a lot more to this than the rule suggests. It's not as simple as just add a side stream, add a few pieces of equipment. This water is not easy to treat, and neither is bottom ash. So it's going to be very interesting how the industry responds. We're prepared to do anything. I tell our customers all the time, if you have enough money, I can do absolutely anything. We have the technology. The challenge is figuring out how to do it economically, and that's where we have to get creative and we have to get smart with how we apply this tech. But my conclusions are fairly obvious. Water quality is going to be an increasing concern. The challenges are site-specific. It depends on the site, the configuration of the equipment, the kind of coal they burn. The days of discharging and purge are going away, whether we like it or not, which is going to necessitate some significant capital investments, such as those listed here. And I like to, every slide deck I do, I like to include jar test pictures just because they're cool. Any questions? Very well. I appreciate your attention. And I have cards. If anybody wants to chat with me after this session, just track me down. I'll be happy to talk to you in more detail about this topic or many other topics if you like. Thank you very much.